potential. The redox potential depends on which of these two sulfur iron clusters is there, number one, but also the protein cloud that we talked about before affecting it. So I want to give you one last example. The example would be, let's take this 4 iron, 4 sulfur complex here, and let's have one of the irons, I just made this one here arbitrarily in the +2 state. And let's say that one electron comes along through the protein, through this complex, and it now it changes it so that, just to name one of them, but again, it's their shared electron. I name this guy down here as a +2. You follow me? And so the oxidation state for the entire complex over here on the right, where it's reduced, would be 2.5, averaging the 2s and the 3s together. Then, of course, when the electron leaves, it goes back to what it was before on the left. But this shows you, I think, a little bit better of what the options are here for these multiple ions and why life might choose these. I mean, you don't have this type of option over here. There's a heme group. The heme has a single iron. It is what it is, +3 or +2 when an electron comes through. This thing on the right opens up an option. And the same would be true over here. There's more options for these 2 ions. So, in the back of your mind, put a little asterisk for this example down here. A protein that we'll talk about in photosynthesis in some of our last lectures. One of the proteins in the Z scheme of photosynthesis is ferredoxin. Ferredoxin has 2 of these 4 iron, 4 sulfur complexes in it, undergoing this type of thing as electrons go through it on their way to make NADPH. So we'll get to that. So it's just something in the back of your mind. All right, here, complex 3, I wanted to make a few comments. So the image here is correct. It's the next one that has some issues. But the first thing is, notice how Leininger has this as a dark green, and this is a lighter green. What that's to imply correctly is the 2 things are coming together to form this cavern from separate monomers. So, participation now, use your hands, okay? You're being graded on this. One hand here is, we'll call it a protomer, but it's actually composed of several subunits. And its sister over here is the other one, and now they're going to intertwine like this, okay? Now, we already talked about they create 2 caverns, correct? But my right-hand thumb, we'll say, is the risky iron-sulfur protein. That's this guy right here. He is actually wrapped around working on this side. And the other guy is wrapped around working on the other side. So I want you to see that 2 things come together to form one functional thing. And they're dependent on each other. You can't just have one. So this guy here is actually coming over. He's actually part of this group over here. And the other thing, and this gets to an error in the next slide, is that these 2 binding sites, QP and QN, what's Q stand for? Coenzyme Q. And here's coenzyme Q binding towards the negative side. These are coming together. Again, when you bring your hands together, the cavern, one of these binding sites in green here is coming from one protomer, and the other binding site, QN, is coming from the other. So not only are the hammers coming from each other, but the parts inside the cavern are coming from each other. Is that clear? So you've got that Q cycle in each cavern participating with QP and QN from each protomer. All right? So now I feel clear. Because when we come over here, they took some artistic license here by saying that this Q cycle, where this thing is binding here and the electron comes down, no, the circuit should be over here because the other binding site is over here. You follow me? So it's like they wrote it here to make it clear, but this is not good science. So really the circuit's coming over here. Now I feel better. And the other thing I wanted to say about this is that the reason why you need to draw it twice, that is the image on the left and then separately as the right, one, to understand how the cycle works, but two, presumably you're starting with 2 electrons with NADH as a hydride. So if you want 2 electrons to go all the way down and make 1 water molecule, then you have to have 2 cytochrome Cs. One can only carry 1 electron at a time. Is that okay with you? So that's why they had to show the image twice, to show 2 electrons on their way to complex 4. Because 1 cytochrome C can't carry 2 electrons. Good? All right. So now that brings to the heart of what we want to discuss today. So I just took our previous slide. I wanted to remind you there's several things happening. These cytochrome Cs are docking. Electrons are going through this first binuclear site. The electrons wind up ending at this second binuclear site. Meanwhile, protons are going up through this red path and through this green path, and there's a little gatekeeper here shuttling 2 protons over to form water. So now we want to tear this apart a little bit. So, right here, this red line indicates the bottom, you're looking at the bottom here of one of the cytochrome Cs. This thing must have information so that it knows to land correctly. Well, there's a K+. What does K stand for in the 1-letter amino acid code? Lysine. So this is not a potassium ion. This is the side chain of a lysine. This would be the epsilon amino group of a lysine. So I'm talking about who's making up the red part right here. And we're going to look, we're down here looking up at this red part. You follow me? And what we're going to see is 9 of these guys, not in a complete circle. It's a little distorted in real life. But they're forming an information grid, if you will. So we're looking at the bottom, and this thing right in the middle is the heme. So we'd be looking at the bottom edge of this heme, right there. So cytochrome C apparently is coming down like a little landing craft, expecting to bind to a complementary ring of negative charges. These would be aspartates or glutamates or something with a negative charge. So that would be this black line here on subunit 2. So there is a ring of corresponding negative charges. But to be honest with you, the Ks, the lysines, only some of them make full contact with the negative charges. The others are a little bit further away. And as you can imagine correctly, in Coulomb's law, the force of attraction is Q1 times Q2 over epsilon r squared. So the distance r between the charges has an exponential effect. So the trick here is that cytochrome C, just one of them, must have enough information to land correctly, not somewhere else on the complex, and then not so strongly that it can leave. This appears to be part of what's going on. I'm sure there's other weak bonds involved, but the point is there's just a very small area where the cytochrome C interacts with subunit 2, just enough to get the job done and leave. Cool? So that's what's happening there. Now, let's look at these two coppers here. These two coppers are bound to the protein. They're not, to subunit 2, they're not floating around freely. And so they're in a complex that looks very similar to the 2-iron, 2-sulfur complex that we had on our previous slide. Only this time, the sulfurs are between these coppers. So these cysteines are part of the protein, side chains of some cysteines, and now they're forming bonds to this, and then the coppers also have bonds to a methionine. Remember the side chain of a methionine? CH2, CH2, S, CH3. Well, this is the S side chain of methionine. Now we're leaving off the CH3 and the other parts. So it's organized like this with a glutamate and some histidines. The point is, all of these residues are part of the protein. And so the electrons are coming through the protein to this binuclear site. That's indicated by this blue arrow here. The electrons are coming through, and then they're leaving because something else wants the electrons even more thermodynamically. So if we look at these two coppers, just like the irons that were in the 2-iron, 2-sulfur complex, their electrons are shared. They act as one. They're so close to each other, they act as one. As with the irons, this allows for differences in oxidation states. Instead of being a +1 and a +2 for copper, it can be somewhere in between. So, here, let's say, is the oxidized. Well, they not say, they know that this is the case. Copper, this guy here, has a charge of positive 1.5, and its brother has the same. And when it picks up an electron, it becomes this. So again, having the two metals so close together allows for oxidation states that are in between. Where's the electron coming from? One cytochrome C, the top, and instantaneously transferred its electron.
Question?
Yes?
So, obviously the amino acid sequence is code for all iron, silver, copper, sulfur. So how do we get these?
They're inserted by enzymes. Another way of answering that, everything is complicated. So, you get a sense of the first binuclear side. Fairly straightforward. Electrons are going through there. Now, let's get tough and tackle the second binuclear site right here. This is where an iron in this heme is so close to this green sphere. This copper is called CuB. These two coppers here, this whole thing is called CuA. But they're so close that analogous to this situation here, they work as a second binuclear site. And this is where the chemistry is occurring that oxygen is going to bind and get reduced to water.